The steady state process. Our first application of the control volume equation will be to develop a suitable analytical model for the long-term steady operation of devices such as long-term steady operation of devices such as turbines, compressors, nozzles, boilers, and condensers. Long-term steady operation. A very large class of problems of interest in thermodynamics analysis related to this topic. This model will not include the short-term transient startup or shutdown of such devices, but only the steady operating period of time. Let us consider a certain set of assumptions leading to the equation of the conservation of the first law of thermodynamics in the rate form for the Q dot minus W dot plus sigma M dot I E H total stagnation E I minus M dot E H total E. For have a steady state process, the control volume does not move relative to a coordinate frame. Does not move relative to the coordinate frame. The no movement for the control volume. The state of mass at each point in the control volume does not vary with time. Of mass at each point does not vary with time. And the last one is as for the mass that flow across the control surface, the mass flux and the state of this mass of each discrete area of the flow on the control mass do not vary with time. as for the mass flow across the boundaries, the mass flux and the state of this mass at each discrete area of flow on the control surface do not vary with time. It is a steady state process. Left here to the coordinate does not move, and the next point is the state of mass at each point does not vary with time, and the mass flux also, and the state of this mass does not vary with time. With this assumption, we can, as an example of a steady state process, consider a centrifugal air compressor that operates with a constant mass rate of flow into and out of the compressor. Constant properties at each point across the inlet and exit duct, a constant rate of heat transfer to a surrounding, and a constant power input, for example. At each point in the compressor, the properties at constant volume with time, and consider a compressor, for example, point 1 as our input and output, work, maybe heat, for example, the rate flow into the and out of the compressor, constant properties at each point, point I, constant properties, and point E, constant also properties. A constant rate of heat transfer to surrounding and a constant periodic power constant periodic power, constant heat rate. This is an example for a steady state process. At each point in the compressor, the properties are constant with time, even though the properties of given elemental mass of air vary. It flows throughout the compressor. It says that, for example, in each point, for example, this point, we have the always same properties. Are same for mass crossing this point. And also maybe different properties, but always we have some properties in each point. Often such a process is referred to as a steady state process. Since we are concerned primarily with the properties of the fluid entering the control volume, however, in the analysis of certain heat transfer problems in which the same assumptions apply, we are primarily interested in the spatial distribution of properties, particularly temperature, and such a process is referred as steady-state process. Since this is an introductory book, we will use the term steady-state process for both the spatial distribution of let me write it another column. Spatial distribution is interest properties refer to steady-state process. Since this is an introductory book, we will use the term steady-state process for both. The student should realize that the term steady-state process and steady flow process are both used extensively in their literature. Steady-state or steady flow process. Let us now consider the significance of each assumption for a steady-state process. The assumption that control volume does not move relative to the control frame means that all velocity measured relative to the control volume does not move relative to coordinate frame means that all velocities measured relative to the coordinate frame are also velocities relative to the control surface. Are also velocities relative to control surface, and there is no work associated with the acceleration of the control volume. There is no work associated with the acceleration control value. And the next assumption, the assumption that the state of the mass at each point in the control volume does not vary with the time requires that the, and also the flux. Therefore, we conclude that the steady-state process, we can write the equation of continuity as this relation, continuity equation. And first law this is due to the first law dE on the steady state process equals to 0. The assumption that values mass flows, and we have also the third assumption. The values mass flow, state, and rate of each heat and work across the control surface. Remain constant requires that every quantity in the equation continuity and also first law be steady with time. This means that application of the continuity and first law for the steady state to the operation of some devices is independent of time. Many of applications of a steady state model are such that there is only one flow stream entering and one leaving the control volume. For this type, for one flow stream, continuity equation and first law m dot I and plus W on control value. Rearranging this equation, we can write as the equation of first law as specific heat and specific work Q plus W and Q cross the control cell system Note that the unit for Q is kilojoule on kilogram from the definition, and Q and W can be thought of as the heat transfer of work per unit mass flowing into and out to the control volume for this particular steady state process. The symbol Q and W are also used for heat transfer and work per unit mass of a control mass. However, since it is always evident from the context whether it is a control mass or control volume with which we are concerned, the significance of the symbol Q and W will also be readily evident in each situation. The steady-state process is often used in the analysis of reciprocating machines, such as the reciprocating compressor or engines. In this case, the state of flow, which may actually be pulsating, is considered to be average rate of flow for an integral number of cycles. A similar assumption is made regarding the properties of the fluid flowing across the control surface and the heat transfer and work crossing the control surface. It is also assumed that for an integral number of cycles, the reciprocating devices undergoes the energy and mass within the control volume do not change. A number of examples are given in the next section to illustrate the analysis of steady-state processes. The next section is about the example of steady-state processes.